Good morning, good afternoon or good evening, wherever you are around the globe. Thank you for joining in for this presentation about 3D printed embedded sensors. What you see in this movie is a flying robot, a so-called robird. As you can see, it has flapping wings and it actually moves quite nicely. But what would be the possibilities if we could also include the sensors and the actuators in the 3D printed part? Already now, large parts of the bird have been 3D printed, but if we could include as well the sensors and actuators, the possibilities would be endless. So this is sort of my dream, and this is something that I try to do in my research. What you see here is a table which is taken from the Trillion Sensors Roadmap report, which actually along the columns has all kinds of sensor applications, and then along the rows shows the different technological platforms. And if you have a closer look at the yellow bar, this is actually the line that is given for 3D printed sensors. And as you can see, this roadmap group has the idea that 3D printed sensors could actually be made for all kinds of applications. So I'm maybe not the only one who believes in these 3D printed sensors. Also, looking at literature, what you see over the last 8 years or so is that there is a quite strong increase in the number of papers which are dedicated to 3D printed sensors. In this talk, I will give you first a few examples from literature. Then we will go into the, let's say, physics of 3D printed electrical conductive materials. I will then continue with giving you some overviews of the sensors that we have been 3D printed over the last couple of years. I will also give you a few examples of where we have used our 3D printed sensors for control purposes, and then I will come up with some concluding remarks. First, looking at the literature of 3D printed sensors, some examples. The group of Professor Jennifer Lewis at Harvard University has been quite active in this field. This is one of their papers from 2016 Nature, which has gathered quite a large number of citations. And the group has been active in developing new technologies, for example here, where there is like a hollow cylinder or sort of needle, which allows you to infuse material, for example conductive material, in a jelly-like structure, and then after solidification you get all kinds of functional structures. For example, these gloves, which allow you to measure the movements of the fingers of a hand, but also structures which are very, very stretchable and so on. Another technology which they have developed is the doping of TPU, which is a soft plastic, a little bit rubber-like plastic with silver particles. They looked at mechanical properties, they looked at electrical properties, but also made a few demonstrators. So what you see here is one band which is actually worn about the upper arm, and which gives you then the opportunity to measure the, let's say, the use of your muscles. And the stronger you activate them, the more LEDs will be lighting up. But also you see these shoe soles with embedded sensors, which allow you to measure the normal force or normal pressure that you see on the shoe sole. So for all kinds of therapeutic purposes. Another group which has been instrumental in basically bootstrapping the field of research is the group of Eric McDonald at the University of Texas in El Paso. The approach of this group is a sort of hybrid additive manufacturing approach, where 3D printed parts are actually equipped with conductive parts which are embedded, let's say, in between 3D printing steps. So they made a quite elaborate system for that. In this photograph you see on the left and the right hand side you see two 3D printers, and in the middle you see a station which is used for embedding of the, let's say, conductive parts, and then there's a robot which basically switches all around the printed parts and makes sure that everything can be manufactured automatically. Things that have been made in the McDonald group are, for example, these let's say functionalized die, where the top face is actually showing the number of eyes that you have on the face of the die. Also, structures have been made which are antennas, so 3D printed antennas, very elaborate shapes, spiraling, but as well sort of sinusoidal along the other side. So these are structures which are very complicated and probably cannot be made with any other technology. On the right hand side you see a device where there are some embedded LEDs, And this structure also has a capacitive sensing capability, so when you touch it, it will change the light of the LEDs. One of the amazing things that they have done as well is making parts for CubeSats. And what you see here is actually a microthruster. So each time you see a light flash, this is actually when in space you would eject a little bit of mass to get a little thrust and let's say adjust the course of the CubeSat. Another group which has been instrumental, I think, is the group of Simon Lay at the Warwick University. What this group has come up with is actually a plastic which is polycaprolactone, which was doped by carbon black. This makes the plastic slightly conductive, as you can see from these examples where we have a blinking or lighted LED. And this can also be cast into filament, and if you have a filament, of course, you can use it in fused deposition modeling, 3D printing. And that's what they have done. So they made examples. Here an example of piezo-resistive sensors, which could be actually put over the hands to measure the activity of the fingers. But also a capacitive example where you have a sort of control path where you can touch one of the capacitive sensors to control some inputs. Or this mug where a capacitive sensor is being used for measuring the fluid level, let's say, of your coffee. In our group, we mostly have looked at the sort of work that is also done in the Simon Lay group. So what we are striving for is 3D printing of structures which don't need any manual assembly afterwards, or as little as possible. So it also means that we have been printing traxels, so track elements of conductive polymers on top of each other. And in doing so, we use a, let's say, regular fused deposition modeling approach, which you see on the left side. In the middle, you see our workhorse, which is a Diabase Engineering H-series 3D printer. Actually, it has a rotating stage, and the rotating stage has 5 nozzles. So in total, we can have 5 different materials in one and the same print. What you see on the lower right is the extruder. The extruder is a flexion extruder. It's a direct drive extruder. This is especially important if you want to print the more flexible parts, because if you are using a regular extruder where the material is basically pushed through a Bowden tube, then you will never get the control that you need for the flexible materials. And you see that this is successful, or at least this is a successful example where we have printed a small structure. The black parts are the carbon doped TPU parts, and the orange part is regular NinjaFlex TPU. And as you can see, the LED is lighting up when we make contact with the battery. At the same time, you see it's very flexible. So this is a very interesting material for our purposes. Okay, what we ran into when we were making these structures is that when we have a certain, let's say, cube we printed, we have a certain height, and we look at the number of interfaces between the different layers. And we make 2 prints, one with twice as many interfaces as the other one. And what we see is that the structure, which has the fewest interfaces, also has the lowest impedance. So that clearly tells you that actually the number of interfaces is determining quite a bit what the impedance will be, and so the interface resistance is an important part. So if you think about these FDM printed structures, you really have to think in terms of the track elements that you have, the traxels, and how they make contact sideways, but also layer to layer, because in both directions you will have a limited electrical conductivity. And if you have a limited electrical conductivity, it also means that you will see a mutual capacitance as well. So if you put this together, actually what you find is that a 3D printed electrical conducting part is actually a network of resistors and capacitors. So once you have this sort of idea of what the material should look like, and once you accept that both the traxels have interface resistances as well as the layers have interface resistances, then of course it's interesting to see what that does in practice. So what you see in this graph, in the upper graph, is when you have a structure which consists of straight traxels, and you connect it on the top left and the bottom right, then the current actually goes diagonally through the structure, because there is no way that there is a shorter path with a lower resistance than going through all the interfaces. However, in the second structure, what you see here we have a meandering structure, and then of course it's more straightforward for the current to go through the lower resistance part, which is through the meandering, and then actually passing one interface and then again taking a meander, because now you will have half of the interfaces. So what happens is that most of the current actually is guided along the edges of the structure, because this gives the lowest resistance path. And this is the infrared image that we took from a sample, so the physical reality, and this is what we see if we use our finite element method calculations, and you see that this resembles the thing quite well. So knowing this, we made a model where we take into account the intertraxal resistance and intertraxal capacitances, and calculated and predicted, let's say, the impedances for a certain structure and a certain connection of the structure. And we compared it to the measurements, and that's what you see in this graph. And you see actually that the measurements and the calculations nicely coincide. So we do think that we have a model here which can help us to understand what the electrical behavior is of this structure. Okay, so we have these complicated behavior of traxal sort of structures, and the anisotropy of the conduction. But despite this, or sometimes even because of this, we have been able to make a large number of sensors in the previous few years. And here you see a sort of zoo of all the things that we have been making, yeah, I will pick out a few of them. So to show you a little bit of what you can do with 3D printed sensors. We first are going to look at mechanical sensing, and for that we first look at piezo resistance. So what you see here in the upper picture here is actually, it's a CID design, and it is a sort of cantilever structure which has a strain gauge on the front side, but it also has a strain gauge on the back side. It's meant to be a tactile sensor, but it can also be used for a flow sensor if you decide to have a somewhat larger flap on top and a somewhat more compliant structure. What you see here is the 3D printed part with the additional connectors, which actually are on both sides. And in the lower graph, or the lower figure, you actually see the measurement setup where we have a linear actuator which can move the sensor, let's say sinusoidally, and then simultaneously we can measure the resistance, and that way we can see what the relation is between the displacement and the sensor output. So that's what you see here. In the top part of the graph you see both outputs of the front sensor and the sensor on the back side. What you see in the middle is actually the difference between the two, and what you see in the lower trace is actually the periodic displacement that we apply to the sensor. What you can immediately see is that for the single strain gauges, there's quite a bit of nonlinearity. So we see not the sort of sinusoidal resulting output, but it seems as if there is like a sort of doubling of the frequency, which has to do with the rather complicated, let's say, piezo resistance of the material. However, by taking the difference between the two, it looks much more like the displacement that we are applying. Also, if you plot the displacement and the change in resistance versus each other, you see for both strain gauges that they are quite nonlinear, and there's also this sort of butterfly hysteresis. However, if we take the difference between the two, we get a rather linear response, and also the let's say the area of the hysteresis curve is much smaller now. So if you put that in numbers, then what you actually see is that your signal to noise and distortion ratio goes from, let's say, a maximum of 7.51 dB for one strain gauge to 18.83 dB. So that's quite an improvement in terms of linearity. Another example of a strain gauge is this actually this sensor which we have developed for measuring the shear and normal forces on the fingers. So this is important, for example, if you look at stroke patients, if you look into rehabilitation and you want to know how much force they can apply, you want to measure the shear force and the normal force, then this structure could be, or this sensor could be interesting. So what we do in this approach, which has been developed by Gijs, is that we take the finger itself as the mechanical component, which of course has the bone, it has the tissue, and it can be deformed depending on how much force you put on it and which direction you put it. So what we came up with is actually a structure where you have two strain gauges around your finger, as indicated in these figures. So this is the actual printed part, and it can be put around the finger like this. And now if you look at the simulations, what happens if you apply a normal force, so you're pressing here, then basically the strain gauges on both sides will see the same deformation. So if you add these two, you will get a stronger signal, but if you subtract them, actually you won't measure so much. However, if you apply a shear force, then the strain gauges are anti-symmetrically strained, and therefore if you now take the difference between the two, you get a signal which is primarily, let's say, representing the shear force. So in this small movie, what you see is that we actually mounted these sensors on fingertips together with some other sensors. And what you see on the screen is actually that when there is like a shear force, you see that there is a going up and down of the signal, which has been provided by taking the difference of the two strain gauges. So this is working, although we still have to work on the, let's say, the quantitative output. Quantitatively it looks good, quantitatively some improvement needs to be made. Now let's look into mechanical capacitive sensing. So what you see here is a shoe sole, and the intention is to make a shoe sole where we can implement sensors which allow us to measure shear forces. And our student Jens Oprel came with this design where we actually have two sort of beams, rather wide beams, but it's still beams, which are sort of suspending an upper part which has a block, let's say, pointing downwards, and on the bottom side there's a block pointing upwards, because what we get this way is that we have the, let's say, the wires of the capacitances quite near to each other, so we can get considerable capacitances, or at least large enough to be measured, while still the larger beams or the higher beams allow for a more compliant structure. So this way we can make a structure which has sufficient compliance as well as a large capacitor. Now, if we move these plates, or actually these are collections of traxels, if we move them over each other, then what you see is that the capacitance between these sets of wires is going to change. And as indicated in the structure, we do have actually in the bottom side, we do have two separate sets of wires. So if we move one way, one of the capacitors could increase and the other capacitor would, or other capacitance would be smaller. So again, taking the difference between these two, we get a relatively nice linear response. What you see here is what they look like in 3D printed form. And in the next slide, what you see is the experimental setup. Again, we use this linear actuator, which we use to periodically move the sensor in shear direction. And what we measure is what you see in this graph. There's still quite a bit of nonlinearity, which we did not directly expect. But then if we look at the displacement versus force graphs, we see actually in this graph that there is quite a bit of hysteresis. Whereas if we look at the capacitance versus displacement graph, we see that this is nicely linear. So we suspect that something has come up with the measurement setup, which makes that we get this weird jumps that we have here, but the actual capacitance measurement is working quite linearly. Another sensor that we have been working on lately is a sensor which is to be used in a operation where prosthesis parts are put into a partial knee replacement. In our case, we try to make a structure which can measure the normal force let's say on the spoon. So what you see here is actually a sensor, let's say side view, where we have three electrodes, and between each of the two electrodes we have a capacitor. But the dielectric between the upper part and the dielectric between the lower part is not exactly the same. So when we press on the structure, the two capacitances will change, but they will not change in the same way. So taking the difference, we can use that as an output signal. What you see here is the CAD design as well as the 3D printed part. And in the next graph, you will actually see what it looks like when we do the measurements. So that's what you have here. So in this graph, you see both the applied force sinusoidally as well as the response of the system. And as you can see, this follows quite nicely. So we did the same thing here in terms of trying to see whether the nonlinearity, remaining nonlinearity would come from the capacitor or from the mechanics. And as it turns out, here it actually comes from the capacitor, but here in this case we have a cap closing capacitor, which has of course a nonlinear let's say, displacement capacitance ratio anyway. Another sort of sensors that we have been looking into are biopotential sensors, and mostly into EMG sensors. So when we activate our muscles, first, of course, there is, let's say, a neural signal which makes that our muscles are going to contract. But when the muscles contract, they produce a voltage. And this voltage can be measured by putting electrodes on the skin. So normally what people use are these silver chloride electrodes, and then through all the different layers in our skin and the tissue which is below the skin and so on and so forth, you still can measure the voltages or the potentials which are generated by the muscles. So this is the normal, let's say, normal silver chloride electrode. This is an array electrode which sometimes is used for high density EMG, and this is the sort of electrodes that we can 3D print. So the black parts are again the conductive parts, the orange part is the non-conductive part. So let's say advantages of 3D printed electrodes are the scalability, the flexibility, and also the customizability. For example, we can make these sort of bands which we can wrap around our lower arms, and we can have multiple EMG sensors and connect them as well to the electronics which we can put in this box. And that way we can actually pick up signals and do something with that. So what you see if you're using these sensors is that they nicely pick up the signals from our muscles. The raw signals has quite a bit of low frequency content due to the 50 Hertz. But if you filter that out, and then you get this signal, here you see the isometric and the isokinetic activations of the muscle. Here you see the power spectrum, and here you see what you get if you take the envelope detection of this signal. So this is nicely showing the signals. Now if you compare that to the silver chloride electrodes, which still is sort of the golden standard, then you see that actually the power spectrum looks quite similar to the ones of the silver chloride. So the PI eTPU is not doing worse actually. And also if you take the muscle activation and increase the effort by the muscle by increasing the force by having a weight, for example, you see that actually the silver chloride and the 3D printed electrodes show rather the same response. So we have used that in this band and have looked at a possibility to take the input of 8 electrodes, put that into a classification machine learning algorithm, and that way we were able to train a network, and using that network we got an output which we used again to control the prosthetic hand or artificial hand, robotic hand, which has been made by the University of Pisa. You see actually doing this that there's quite a nice recognition of the gestures, and the robotic hand is nicely replicating the movements of the actual hand. Okay, now coming to some applications. This is a cantilever beam in which we have implemented strain gauges again, one pair at the base and one pair in the middle. And we have a possibility to apply an additional force on, let's say, in the longitudinal direction of the beam. So if you look at your beam equation, that provides an additional term, and this term actually makes that you get stiffening of the beam. So what we do now, we use the sensors, and we have this mechanism to strain the beam and change the stiffness of the beam. So with the sensors, we pick up the movement of the beam, and then we can apply a periodic change of the, let's say, this force Q in order to have a periodic modulation of the stiffness. And if you do so, you can control that in such a way that either you are going to get let's say, a higher damping, or you get a lower damping. And so this way, what you see in the graphs is actually the change in, let's say, in the decay time, depending on how we use the control. So we have now a system with a, let's say, controllable stiffness, which leads to controllable damping. So after all these examples, some concluding remarks. Finally, as a conclusion, multi-material 3D printing has great promise, I think, for embedded sensing, and I hope you are now as convinced as I am. Also, there's quite a bit of a learning curve because of the complexity of the materials, the non-linearities, the anisotropy, etc. Also, we have proposed and also realized a range of sensors. We have shown also that you can do some control applications with those sensors. And of course, there's still something to be decided. It would be nice to have higher resolution, to have better conductive filaments, and so on and so forth. But I think all is in development and things are looking quite promising for the near future. Finally, I like to acknowledge all the input of all the students and colleagues and PhD students which have worked with me, especially my PhD students, which you see here with the underlined names, have done a tremendous job in getting all these sensors done and in coaching all the bachelor and master students. I also like to acknowledge the funding from the EU, from the ERC, from the NWO in the Netherlands, as well as the 4TU organization for providing us with funding for this research. This will end my talk, and I'm happy to take any questions. Thank you for your attention.